Welcome to Lecture 3.4, Direct Products. Previously, we looked for smaller groups lurking inside a bigger group, and we called those subgroups. Exploring the subgroups of a group gives us insight into its internal structure. In contrast, the next two lectures are about the following two topics. Number one, direct products. That's what this lecture is on. This is a method for making larger groups from smaller groups. And two, quotients. This is a method for making smaller groups from larger groups. Before we begin, we'll note that we can always form a direct product of two groups. In contrast, we cannot always take the quotient of two groups. In fact, quotients are restricted to some pretty specific circumstances, as we shall soon see, although that will be not in this lecture, but the next one. I'm going to show you two ways to think about the direct product of groups, both algebraically and visually, and I'm going to start with the algebraic because I think it's simplest. If A and B are groups, then there is a natural group structure on the following set, A cross B. This is the Cartesian product consisting of all things in A and all things in B. So think about what this means, natural group structure. How would you multiply two things like this together? Well, here's the answer. The direct product of groups A and B consists of the set A cross B, that's Cartesian product, a set of all these, and the group operation is done component-wise. So if A, B, and CD are elements in the Cartesian product, then AB applied to CD, or multiplied, is just AC times BD. We call A and B the factors of the direct product. Now it's important to point out that the binary operations on A and B could be different. Now I've denoted them both just by multiplication, although this is a little bit sloppy because one of them might be just plain old star, might be multiplication, might be function composition or something else, and the other one might be addition. For example, in the following direct product, D3 cross Z4, let's think about how you would multiply these two elements, R squared 1 and FR and 3. So you just multiply them component-wise, so this is R squared FR, and then the operation in the second component is addition, so it's 1 plus 3, and that becomes RF and 0. Note that these elements do not commute, because if I want to multiply these two ordered pairs in the reverse order, I get FR cubed and 3 plus 1, which is F0, so this is not equal to that. Here's the second way that I want to present the idea of a direct product, and that is visually. And let me start with a simple example of cyclic groups. So suppose we have Zn cross Zm. So imagine a slot machine with two wheels, one with n spaces, numbered 0 through n minus 1, and the other with m spaces, numbered 0 through m minus 1. The actions, and when I say actions, I mean in our original sense of our unofficial definition, are spinning one or both of the wheels some number of times. So each action can be labeled by where we end up on each wheel, say ij. And so here's a picture of this. Let's suppose that we have this wheel right here. Maybe this is slot I, and this is slot I plus 1, and this is I minus 1, dot, dot, dot. Maybe this is, and maybe right next to it is a wheel that we can spin. And maybe we ended up at j, and this is j plus 1, and j minus 1, and so forth. So you can think of elements of the cyclic group Zn cross Zm as all actions of spinning both of these wheels, which of course is in bijection with the configurations. So this configuration of being at wheel I, or slot I on the left and slot j, corresponds to an action. In the more general case, we lose the slot machine analogy. So here's an example of an element in D4 cross Z6, But in general, you can think of it as having one group over here on the left, D4, the other group on the right, Z6, and elements in the direct product correspond with something in here and something in here. So, for example, pick an element r squared in D4, and pick an element, say, 4 in Z6. So the key idea is that the direct product of two groups joins them so they can act independently of each other. Let's continue the visual exploration of direct products by looking at the Cayley diagrams. But first, an important remark. Just because a group is not written with this direct product symbol does not mean that there isn't some hidden direct product lurking behind the scenes. For example, V4, the Klein 4 group, is secretly C2 cross C2. Remember the two light switch group? You can think of V4 as this direct product. Here are some other examples of direct products. So here is the Cayley diagram of C3 cross C3. Here's C3 cross C2 in the middle, and on the right is C2 cross C2 cross C2. Perhaps even more surprising, the group C3 cross C2 is actually, that's this group here, is actually isomorphic to the cyclic group C6. If you're having trouble seeing why that's the case, note that the Cayley diagram for C6, if I use generators r squared and r cubed, is the same as the Cayley diagram for C3 cross C2 above. We'll understand this better later in the class when we study homomorphisms. But for now, we want to focus our attention on direct products. So if we have two groups and we're taking the direct product, then each group has an identity element. And those identities might be, well, they are different, but they might look entirely different. One of them might be a 0 if it's under addition, and the other might be a 1 if it's, say, under multiplication. So let's denote these two identities by EA and by EB. Given a Cayley diagram of A with generators A1 up to AK, and a Cayley diagram of B with generators B1 up to BL, we can create a Cayley diagram for the direct product A cross B as follows. So as a vertex set, we take the Cartesian product, that is ordered pairs of things in A with things in B, and then as generators, we take K ordered pairs for the generators in A. Those are of the form one of the generators in A with the identity in B, and then we take L ordered pairs of generators corresponding to those in B of the form the identity in A with a generator of B. Frequently, it is helpful to arrange the vertices in a rectangular grid. For example, here is a Cayley diagram for the group Z4 cross Z3, constructed using this method above. So notice that there was one generator in both the Cayley diagram for Z4, that's a copy of it is right here, and for the Cayley diagram of Z3, a copy of that lies right here. Let me ask you a question now. What are the subgroups of Z4 cross Z3? So take a look at this diagram, and I encourage you to pause the lecture and see how many of them you can find. And then I'll show you the answers. Okay, so let me show you at least how many there are first. Are you ready? There are 6. Did you find them all? If not, I encourage you to pause the lecture and see if you can find a couple that you missed. So let me show you what they are. Of course, there's the entire group, Z4 cross Z3. That's always a subgroup of any group. There's the trivial group. So you can think of it as the element 0, 0, or you can think of it as this subgroup of Z4 cross this subgroup of Z3. There's a subgroup 0 cross Z3, so that corresponds to these 3 elements. So in other words, ordered pairs consisting of 0 in the first coordinate with something in Z3 in the second coordinate. So that, of course, is isomorphic to Z3, meaning it has the same structure. Now, if there's a subgroup like this, there's a corresponding one that looks like this, Z4 cross 0. So this sits right here. It's the ordered pairs consisting of anything in Z4 in the first coordinate, 0, 1, 2, or 3, and 0 in the second coordinate. So now there are actually two more subgroups that are a little bit trickier to find if you just look at the diagram. So let me show you what they are. Z2 cross Z3. Now I have to point out that I'm being a little bit sloppy here. When I say Z2, I mean the subgroup of Z4 consisting of the elements 0 and 2, which is isomorphic to Z2. It's not actually the elements 0 and 1 in Z4. That's not a subgroup because 1 is a generator. So in the Cayley diagram, Z2 cross Z3 corresponds with all ordered pairs where the first element is either 0 or 2, that is, it's even, so, and the second element is anything in Z3. So that's this row with this row. Notice that this is indeed a subgroup. If you take any one of these 6 ordered pairs and you add it to any other one, you still get an ordered pair in the original set. The first entry is going to be even, and the second entry is going to be in Z3. Now finally, there's one more subgroup. That's Z2 cross 0. So that is the subgroup consisting of just these two elements, the identity and 2, 0. So this, of course, is a subgroup of size 2, because if you take this element and you add it to itself, you get back to the identity. Let's make some remarks motivated by that last example. So the first remark is that if we have a subgroup of A, call it H, and a subgroup of B, and we take the direct product of those subgroups, then that is going to be a subgroup of A cross B, the direct product of A and B. And think about why that's true. Take ordered pairs of things in H and things in K, and as you multiply them together, in the first coordinate, you still get something in H, and the second coordinate, you still get something in K. And for the last example, Z4 cross Z3, all 6 subgroups had this form. However, this is not always true. That was just a small example. For example, consider the group Z2 cross Z2, which is really just the Klein 4 group, V4. Since Z2 has 2 subgroups, the following 4 sets are subgroups of Z2 cross Z2. There's the entire subgroup. There's 0 cross 0, which is just the identity element. Z2 cross 0, this is the subgroup generated by 1, 0. And then 0 cross Z2, which is the subgroup generated by 0, 1. However, there is one subgroup of Z2 cross Z2 that is missing from this list. Can you think of it? It's the subgroup generated by the element 1, 1. It contains these two elements, 0, 0 and 1, 1, but it is not the direct product of 2 subgroups, something in here and something in there. That's interesting, isn't it? Well, here's an exercise. What are the subgroups of Z2 cross Z2 cross Z2? And here's a Cayley diagram. And here I'm going to write the elements instead of ordered triples, A, B, C, with all the commas and parentheses, just as A, B, C. So binary strings of length 3. You can think of addition as doing it component-wise, modulo 2. And my hint are that there are surprisingly 16 subgroups in here. So I encourage you to pause the lecture and see if you can actually come up with a complete list, because it's really, really easy to do this exercise and to skip a few. So give it a shot and make sure that you indeed do get 16. Welcome back, or for those of you who did my suggested exercise. So here is yet another way to view direct products visually. This is not needed, but it helps motivate the concept. And the idea is that one can construct the Cayley diagram of a direct product using the following so-called inflation method. So to make a Cayley diagram of A cross B purely from the Cayley diagrams of A and B, you start with the Cayley diagram for A. And then within each node, inflate it into a big bubble. Just blow it up, and inside of it, place a copy of the Cayley diagram for B. And use different colors for the two Cayley diagrams. Now, pop those bubbles. So remove the inflated nodes of A while using the arrows of A to connect the corresponding nodes from each copy of B. That is, remove the A diagram, but treat its arrows as a blueprint for how to connect the corresponding nodes in the copies of B. Now, you probably aren't quite following this because it's a little bit wordy, so let me start with a picture. Take the cyclic group Z2, and we are going to construct the direct product Z2 cross Z4. So that means A is going to be Z2, and B is going to be Z4. So to begin, we start with the Cayley diagram for A, which is Z2, which we have right here. And next, we are going to inflate each node, both of these nodes, and place inside of it a copy of the Cayley diagram for B, which is Z4. So let's do that now. There it is. So with this picture, we're actually doing the last two steps, or most of the last two steps. So we inflated each node in the original diagram, and we stuck inside a copy of the Cayley diagram for B, that is Z4, and then we also used the arrows of A to connect the corresponding nodes from each copy of B. So we connected the corresponding nodes in the copies of B together, and now we just are going to burst these two bubbles, and we get the Cayley diagram of the direct product group Z4 cross Z2. And again, this method is not actually needed, but I think it helps just as an extra visualization tool just to get you some extra intuition. Okay, so let's discuss some properties of direct products. So recall the definition from the previous lecture. A subgroup H of G is normal if every left coset is a right coset. In other words, XH equals HX for all x's in G. And we denote that with this little triangle inequality. Assuming A and B are not trivial, meaning they contain more than the identity, then the direct product A cross B has at least 4 normal subgroups. One of them is, of course, the trivial subgroup, the ordered pair containing just the identity elements. One of them is the entire group. Now those two are always normal subgroups, but here's 2 more. This is A cross the identity and the identity cross A. And let's see why these things are normal. Let me start with this one here. Let me just take an arbitrary element, A, and I'm going to write it as E instead of E sub B. And let me conjugate it by some other element. So let me think what I want to call this one. How about CD inverse and CD here. Now it's easy to see that the inverse of this element is just C inverse D inverse. So I can write this as, so everything component wise, C A C inverse, and then D E D inverse. And then what do we know about these elements? So this first element is obviously in A, because A and C inverse are in A. And A is a group. So this thing is in A, and this second element is just the identity of B. So we can write this as something in A, let's call it A prime, with the identity in B. And again, we can do that because we know this is in A, and the second one, of course, is the identity. And so this is in A cross the identity of B. I guess now I'll stick a little B there to denote the identity in B. And so therefore, this subgroup is normal. Now remember which one of our 3 methods from the previous lecture we used. We took an arbitrary element in here, we conjugated it, and we showed that we ended up back in here. So sometimes we abuse notation, and instead of writing this cumbersome thing, we'll write A is a normal subgroup of A cross B. Now obviously A is not even a subset of A cross B. This is a group, and this is an ordered pair of group elements. So whenever we write something like A is a normal subgroup of A cross B, we're really implying this thing here is a normal subgroup. And similarly, B being normal in A cross B means this is normal in A cross B. Here's another observation, and in quotes, A arrows are independent of B arrows. So remember in the previous Cayley diagrams when we had these rectangular grids, if we followed a red arrow, or we followed, say, a red arrow horizontally in one direction and then a blue arrow vertically, that was the same as doing the blue arrow and then the red arrow. So things in A commute with things in B. That's the casual way to say this. So let's highlight that as a main observation. In a Cayley diagram for A cross B, following A arrows neither impacts or is impacted, should I say nor? Probably nor, is impacted by the location in group B. And this is if you think about it using that inflation method that we did in the previous slide. Algebraically, and I encourage you to always think of things algebraically with direct products because it's arguably simpler, this is just saying that this generator, A, and the identity applied to this generator, the identity in A and B, which of course is the element AB, can be written in the opposite order. So following the A arrow and the B arrow is the same as following the B arrow and then the A arrow. Finally, I want to finish this lecture by saying a word about multiplication tables of direct products. There's also a nice little visual that goes along with this, but it is also optional. And as before, I will do an example with a simple set of groups, and it should be clear how to generalize this. So we will do Z4 cross Z2. So we start with the multiplication table for the group Z4, and that's right here. I know it's really an addition table because our operation is addition, but we call these things multiplication tables for any group. And then we inflate each one of these little cells to contain a copy of the multiplication table of Z2. So I think the picture should be clear as to what I mean by that. So a multiplication table for Z2 is just this 2 by 2 thing that has zeros and ones in it. And then from here, and finally, we join the little tables and element names to form the direct product table for Z4 cross Z2. And of course, we can do this for much more complicated groups, but I think this example should motivate the concept.